Okay, ladies and gentlemen, this is going to be chapter 4.2 electric field charges. Looking at the first question here, what do they want from you? What is an electric field? Number one, a region around a wire carrying an electric current in which a compass needle experiences a force. This is actually a magnetic field. A region in which an electric charge experiences a force. This could be logical. A region in which an electric charge is attracted to the Earth's gravity, not possible. A region through an electric-magnetic radiation, not possible. Okay, so it's B. To be more exact, it's actually a region where a positive charge experiences a force here. So then to be here, next question, a negatively charged rod is held close to one side of a metal sphere. The other side of the sphere is earthed. Which diagram shows the distribution of the charges of the metal sphere? You can see that all of them are negatively charged. If all of them are negatively charged with the earth wire here, what's going to happen is it will actually repel all the negative charges downwards. So looking at this donkey is going to be the answer. It will attract the positive charges and repel the negative charges here. Alright. Then question number 3, a cell is connected to a lamp as shown. Figure a charge 4 coulombs, this is going to be a Q, flows through the lamp in 2 seconds. What is the direction of electron flow of the lamp, and what is the current in the lamp? Now, first and foremost, you have to understand that electrons flows from negative to positive. So obviously it's going to be from left to the right here, right? It's going to be from left to the right here. And after that, current is going to be Q equals to IT. I would have been equals to Q over T here, which is essentially going to be 4 divided by 2, which in this case will be A as the answer here, guys. Alright, then moving on. A metal conductor is connected to a battery. Which statement describes the current in the metal conductor? It is a flow of electrons from the negative to the positive terminal. Logical. It is a flow of electrons from the positive to negative, not logical. It is flow of protons, is not logical. Protons will not flow. Only free moving electrons can flow. So A is going to be the answer here. Alright, then question number 5. In an electric circuit, 40 coulombs of electric charges passes a point in 5 seconds. What is the current here? Q equals to IT, right? So I will be equals to Q over T here. It will be 40 divided by 5, which is obviously going to be 8 amperes in this case here. Alright, then question number 6. Each diagram shows 2 charged metal plates. Which diagram shows the pattern and direction of the electric field? Always remember that electric field travels from positive to negative charge. This illogical, positive to negative, nope. So it's going to be donkey for this answer here. Alright. Then moving on to the next part here. Figure 9.1 shows a conducting ball that oscillates between 2 charged plates. So you can see that there is like a insulating thread, there's a ball here, there's a positive charge, negative charge, and it oscillates between these 2 plates here. The ball repeatedly strikes each plate in turn. Explain in terms of charges on the ball why the ball moves to the positive plate after striking the negative plate here. So basically this question here, you have to understand that this ball, as soon as it hits either one of the plates, right, it will become positively charged or negatively charged, you know. So when it becomes positively charged, let's say for example it strikes the positive plate, becomes positively charged, it will be repelled by the positive plate and strike the negative plate here, where it will then become negatively charged and the whole thing will keep repeating itself. So from here you have to mention that plate charge moves to the positive plate after striking the negative plate. So at first it is negatively charged, right? It goes from the negative plate to the positive plate, right? So meaning to say it was first negatively charged. The ball is first negatively charged, then it is repelled by the negatively charged plate and strikes the positively charged plate. This causes the charge on the ball to become positive and is yet again repelled and strikes the negatively charged plate again. Okay, so this is the concept here. You're supposed to say that the ball is first negatively charged, it is repelled by the negatively charged plate and strikes the positively charged plate. This causes the charge on the ball to become positive, then yet again is repelled and strikes the negatively charged plate again. Okay? Then after that, state which particle moves through a sensitive ammeter and the direction which it moves from. Whenever they talk about any particle that moving in the ammeter obviously measures current, right? And the only thing that causes current flow is because of electrons, right? So you're supposed to mention that electrons flow through the ammeter. It moves from the negatively charged, what's it called? Negatively charged power supply. From the negatively charged power supply, not negatively charged power supply, it moves from the negative terminal to the positive terminal. Okay. Then after that, for each complete oscillation of the ball moving between the plates, a charge of 8.5 times 10 to the power of negative 10 coulombs is transferred from one plate to another. The frequency of oscillation is 4 Hz. 4 Hz means to say it completes 4 oscillations per second. Calculate the current shown in the sensitive ammeter. So I'm basically looking for current, right? But I'm given Q and frequency here. So in order to find this I here, I'm supposed to employ the Q equals to IT, but I'm missing the T component. I can find the T component by understanding that frequency is equals to 1 over period, right? So in other words, time would be 1 over frequency, which is going to be 1 over 4, which is 0.25 seconds. With this 0.25 seconds, I can substitute it into here, and then, using I equals to Q over T, it will be essentially 8.5 times 10 to the power of negative 10 divided by 0.25 here. So if you press everything into the calculator, 8.5 times 10 to the power of negative 10 times 4 essentially, right? You're supposed to get 3.4 times 10 to the power of negative 9 amperes. Right? Then finally here, a lightning conductor protects a tall building and the people in it against damage and injury caused by lightning strikes. The lightning conductor is a very long strip of copper that is attached to the side of the building. At the top of the building, the strip of copper is connected to a vertical metal pole at the bottom of the building. It is buried in the ground. Figure 7.1 shows a thundercloud passing over the building. You'll notice this in most tall buildings. We call it the electrical pole, right, or metal pole, whatever you call it. What it essentially does is it will usually attract the lightning strikes to be struck upon this metal pole, which will allow all the excessive amount of current and electrons that is supposed to be redirected to the ground here. So it kind of protects whatever electrical devices that is in this building here, right? Then from here, they say that the bottom of the thundercloud is negatively charged. As the cloud moves closer to the building, the top of the metal pole becomes charged. The top of the metal pole becomes charged, obviously it's going to become positively charged. State the sign of the charge at the top of the metal pole. Explain in terms of particles involved how it becomes positively charged. So my statement is obviously the top of the metal pole is positively charged. And I need to explain why it is positively charged now. It is simply because the negative charges from this cloud here is repelling all the negative charges from the pole down to the ground. So you're supposed to mention that the negatively charged cloud repels all electrons from the metal pole to the ground, or earth wire, down the ground, to the ground via the earth wire. Right? I'm supposed to mention something like this here. Okay? Then moving on to the next part here. As the cloud passes over the building, a lightning strike occurs at the charge of 0.84 coulombs, flows through the lightning conductor. The charge flows for this amount of time. calculate the average current. It's very straightforward. Yet again, it's Q equals to IT. I would be equals to Q over T here. In this case, it will be 0.84 divided by 3.5 times 10 to the power of negative 5 here. Press all of this into your calculator. 3.5 times 10 to the power of negative 5. You'll get 24,000, which if you change it to standard form will be 2.4 times 10 to the power of 4 amperes, guys. Right? Just press everything into the calculator. Then final page here is suggested that the current in the lightning conductor could be measured by connecting a laboratory ammeter between the poles of the copper strip. State one reason why this cannot be successful. This is obviously impossible, right? Because the laboratory ammeter can measure how much? Maximum of 5 amperes of current. Thunder strike is well above that 5 amperes of current. So you're supposed to say something like the thunder current from the lightning is much higher than the readable amount from a ammeter. In fact, in reality, when thunder does strike and you're reading the current with an ammeter, the ammeter will burst into 1,000 pieces. The copper strip has a large cross-sectional area. State how increasing the cross-sectional area of the copper strip affects its resistance. Obviously, the larger the cross-sectional area, increasing the cross-sectional area decreases the resistance of the copper strip. Okay, so this is the first exercise here. All right, and moving on to the next exercise here. A positively charged rod is held near to but not touching, is not touching an uncharged metal sphere. The sphere is briefly now connected to the earth. The rod is removed. Which statement about the charge on the sphere is correct? So basically, you connect it to the earth wire, then after that you remove it, right? Briefly connect it, then you remove it. So which statement is going to be correct? It is charged negatively because the negative charges have moved from the earth to the sphere. This is possible. Basically, you have a positively charged rod, and then you have a sphere that is connected to an earth wire briefly, right? So briefly, maybe it was removed first before the positive charge rod lah. So this could be possible. It is charged negatively because positive charges move from the earth to the sphere. No, this is not possible. The earth wire can only allow electrons to flow. It is charged positively, definitely not possible. It is charged positively, not possible as well. So A is going to be the answer because it is attracting all the negative charges from the earth wire. Which diagram represents the electric field due to a negatively charged conducting sphere? Obviously B is the answer, no explanation here. Oh god, I mean A is the answer, guys. The electric field is going to go in a negative charge and out from a positive charge. Then question number 3, there is a current in the metal wire. Which particle moves and causes this current? Obviously it is electron, nothing to explain again. Which circuit shows the direction of the convectional current I and flow of electrons? Current always flow from positive to negative. Electrons always flow from negative to positive. So B is going to be the answer. Current flow positive, negative. Electron flow negative to positive here. Right. Then after that, moving on to this next part here. State what is meant by the direction of an electric field. Now for those who do not know, an electric field, right, is basically a force experienced by a positive charge when placed near a sphere. So basically what the scientists did was, right, if let's say this is a positively charged thing, right, a positively charged sphere or whatever, right, scientists, they'll actually place another small positively charged atom or whatever sphere here, right? And they noticed that this positively charged sphere will be repelled outwards, and this gave rise to these electric fields, guys. That's why I always see that electric field is going from positive to negative. It's the same for a negative charge as well. Scientists will place a small positive charge here, and they notice that they are actually being attracted inwards. That's why this gives rise to the electric field, that positive goes outwards and negative goes inwards. So from here, you're supposed to mention it is the direction experienced by a positively charged particle. Okay. Then after that, figure 9.1 shows a pair of oppositely charged metal plates with the top plate being positive. The electric field between the plates is uniform. Draw lines on 9.1 to represent this uniform sphere. Add arrows to these lines to show the direction of the field. Obviously, like I mentioned, it's going to go from positive to negative, right? So when you're drawing this electric field, make sure that the spacing is at least from the eye level equal to each other. This indicates that they have uniform electric field strength, guys. Alright. Then after that, figure 9.2 shows a very small negatively charged oil drop in the air between a pair of oppositely charged horizontal metal plates. The oil drop does not move up or down. So basically, from here they say that this thing here could be either positively charged and this is negative charged, or it could be on top is negatively charged and at the bottom is positively charged here. Now today, if this is the case, right, you have to understand that in order for this oil droplet to be stationary, the upward forces must be equals to the downward forces here, right? And if the upward forces are equals to the downward forces, logically speaking, the downward force is obviously going to be its weight. And since it is placed in a electric field, right, it is obviously going to experience a electric field, electric force upwards, right? So in order for this to have an electric field upwards, the top part must be a positively charged plate and the bottom must be a negatively charged plate. This way, the negative charge can repel this outwards, the positive charge can attract this negative droplet upwards, right? So from here, if you can understand the concept, you can tackle the question. Suggest in terms of forces why the oil droplet does not move and up or down, right? So in terms of forces, the upward electric forces are equals to the downward forces due to its weight. And this is how you're supposed to say it. Obviously, there is no resultant forces, right? Without losing any of its charge, the oil droplet begins to evaporate. So if it begins to evaporate, it means to say the weight is starting to decrease, right? So if this thing here starts decreasing, obviously there will be a resultant force upwards. State and explain what happens to the oil droplet. I'm going to say that the oil droplet starts moving upwards as the upward forces is greater than the downward weight. Alright, so basically you mentioned that the weight is decreasing because it's evaporating, right? So then obviously it's going to move upwards in this case here. Okay. Then second question, figure 8.1 shows a uncharged conducting sphere on an insulating stand placed close to a positive charge rod. So this thing here is chargeable, right? And there's a positive charge rod here. Obviously it's going to become negative, right? So the rod and spheres are not moved. Describe how to charge the sphere using a wire connected to the earth and explain whether the sphere becomes positively charged or negatively charged. So first and foremost, this question here is basically asking about charge induction, right? In order for this sphere to be negatively charged, what's going to happen is we have to connect it to an earth wire, right? This will allow the excessive amounts of electrons to flow upwards. When the excessive amount of electrons flow upwards, what's going to happen is it's going to become negatively charged. And then after that, we have to remove this first before we remove this. right, then the electrons will be stuck in this metal sphere. So first and foremost, I'm going to state that the sphere will become negatively charged. And how am I going to do that? By connecting the earth wire to the sphere and removing the earth wire before removing the positively charged rod. This prevents the electrons from escaping down back through the earth wire. Okay, so I was supposed to mention something like this lah, right? Obviously the sphere will be negatively charged. By connecting the earth wire to the sphere and removing the earth wire before removing the positively charged rod, this prevents the electrons from escaping back down through the sphere here, the earth wire here. Okay, then after that, the final part here, figure 8.2 shows a small black circle that represents a positive charge. Draw the pattern and direction of the electric field. For me, if I'm asked to draw this, I like to draw like crosses here, a cross here, then another cross here. Oops. Right, this indicates that they have uniform electric field strength. Then just draw arrows that are pointing outwards because it's a positively charged rod. And finally, a charge of 7 coulombs flow along a wire for 5 minutes. Calculate the current in the wire here. I have Q, I have T. Just make sure to change this into seconds, which is obviously 300 seconds here. I will be equals to Q over T. In this case here, will be 7 divided by 300. Press that into your calculator, 7 divided by 300. You'll get 0.023. 0.023 amperes. Okay, and moving on to the final exercise here, right? What do they want from you? Question number 1. A metal sphere is charged by induction, so there's charges already, all right? There are 4 stages, the W, X, Y, and Z in this process. W is a charged rod is brought near to the sphere. The sphere is earth. The rod is taken away from the sphere and the earth wire is removed. In which order should the 4 stages be carried out? Now this is a very common IGCSE question. Now you have to always remember you're supposed to remove the earth wire first before you remove the positively charged rod. So it should be Z then Y. So yeah, I think anything that has Y first is definitely unacceptable. Okay. So then after that, it's a matter of whether it's which one is first, right? A charged rod is brought close to the sphere is earthed. Yeah, B is obviously going to be the answer in this case. Z, remove first, is definitely impossible. This one, remove before you bring the thing close, is impossible. B is the definite answer here, guys. Alright. Which electric quantity is defined in terms of energy supplied in driving charges around a complete circuit? In terms of energy supplied in driving charges. Oh, this is obviously electromotive force, right? Electromotive force is the thing that is responsible for driving current in the circuit. Yeah. Then a student rubs a plastic rod with a cloth. The rod becomes positively charged. What has happened to the rod? In order for it to become positively charged, the electrons must escape, right? So basically, it has lost its electrons, right? Only then can you become positively charged. So C is the answer here. Which quantity is measured in coulombs? Obviously, is going to be charge. Current is in amperes. Electromotive force is in volts. Power is in watts. Then question number 5 here. An isolated metal sphere is positively charged. It is then brought near to another isolated metal sphere that is neutral. What happens to the charges on the neutral sphere as the positively charged is brought close to it? If it's brought close to this sphere here, what's going to happen is all the negative charges will be towards the left and the positive charges will be towards the right. So some positive charges will move towards the left, no. Some positive charges will move towards the right, and some negative charges will move towards the left, logical. Move towards the right, but negative charges do not move, not logic. Yeah, this question here, you're supposed to understand that the positive charges are actually not supposed to move because only free moving electrons are supposed to move. So donkey is going to be the answer here. And finally, describe the movement of charges that cause an object to become positively charged. Basically, like I mentioned, it is losing electrons only. It can become positively charged, right? Electrons from the object is removed or flows outwards or anything that is logical, right? On figure 10.1 shows a negatively charged rod held over an uncharged metal sphere. On figure 10.1, add positive and negative charges to represent the results of the movement of charges within the sphere. Obviously, the positive charges will be on top, the negative charges will be at the bottom. Now, be very careful when you're drawing these kind of things because it is uncharged initially, right? It means to say that the positive charges will be equals to the negative charges. Meaning to say, if you drew 3 positive charge here, you have to draw 3 negative charge. If you drew 4, you'll have to have 4 negative. If you drew 5, then you'll have 5 negative here because it is uncharged. Uncharged means to say they are neutral. Means to say positive and negative are supposed to be the same. Okay? After that, describe the action that must be taken to obtain an even distribution of positive charges to the surface of the sphere. Right now, if I want to have even distribution to the surface of the sphere, it's obviously charge induction. Yet again, you can see it's 2 marks here. You have to understand that it is that whole process again, right, of charge induction. First, place the connect the metal sphere with an earth wire. Bring the negatively charged rod close to the sphere and remove the earth wire before removing the charge rod. This is essentially charged by induction, guys. All right. So finally, not finally, second last part here. State in terms of their structure why metals are good conductors of electricity. Anytime anything is a good conductor of electricity is simply because there is free moving electrons in the metals. Okay, it's always because of free moving electrons. This is the reason why heat can be transferred and electricity can be transferred as well. Okay. And moving on to the real final question here. A uncharged conducting metal sphere rests on insulating support. Figure 10.1 shows the plate and a positively charged insulating plastic sheet placed on top of the metal plate. So this is a positively charged plastic sheet that is placed on top of a metal plate here. Describe any flow of charges that take place when the plastic sheet is placed onto the metal plate. Obviously, the electric negative charges will be attracted upwards, right? So you're supposed to say negatively charges are attracted upwards. Okay? The negative charges are obviously going to be attracted upwards. Okay? Then after that, on figure 10.1, draw how charges are now arranged in the metal plate. Since it is on an insulating support, it means to say it's supposed to be neutrally charged. So for however much negative charges you have drawn, just draw the same amount of positive charges at the bottom. Okay? Then state and explain if this arrangement of charges helps to keep the plastic sheet in place. Obviously, it definitely helps, right? It helps keep the plastic sheet in place. Then your explanation is because opposite charges attract, right? This is obvious. Then after that, figure 10.2 shows 2 uncharged conducting spheres suspended on an insulating thread. The spheres are now both given positive charges. They're both positive charges here. On figure 10.2, draw a possible position for each of the sphere and the thread. Since they are both positively charged, then obviously both of them will be repelling each other lah, right? And after that, you're supposed to explain the position you have drawn. Positive charges repel each other. Or you could say something like charges repel each other. Okay, and that's 4.2.